各位同学，大家好哦。那我们今天开始上课。So we are going to start our class for today. And last time we talked about BLUE, which is the best linear unbiased estimator. So in some sense, you can think of the estimator, the universe of the estimator, and think of it as a subset of the universe. So we were talking about a subset of the estimators that is linear and unbiased. So in fact it's a very limited subset of the estimators. And today we are going to talk about maximum likelihood. So take a look at this word, maximum likelihood. We have talked about the concept of likelihood many times before. And in this chapter, this is the most formal definition and most formal way of describing the likelihood. And therefore, uh, it will be used in the estimation of a parameter. But recall that we did it for what? We did it for discrete cases. If you recall what we have learned in before the midterm, we talked about the detection problem, which is discrete cases, right? For example, you have H1, H0, or even you have multiple hypotheses where you have H1, H2, H3, H4, so on and so forth. So as a result, we did it for maximum likelihood detection. Now we are doing estimation. That estimation means we are using it for estimating a continuous parameter. Okay, so let's get started, and we have to start slow because the concept of likelihood is a bit abstract. It's not that intuitive. And many people will misunderstand it as probability density function, but in fact it's not. It is not. Okay, uh, so let's first get a little get a little bit reading on what the concept is saying. We now investigate an alternative to the MVU estimator, which is desirable in situations where the MVU does not exist or cannot be found. So, if you remember, when we talk about BLUE, we were talking about a very limited subset of the estimator. And as a result, as I said, for example, if you like to do a DC level problem or you want to do a Gaussian noise problem, that is doable. That is possible for BLUE, but in many cases, it may not exist. If you get a complicated signal model or complicated parameter, then it may not exist. Therefore, we have doubts about how we do it, right? How we can do it. Then one way is to base on the maximum likelihood principle. Based on the maximum likelihood principle. And also be aware that this is in fact, in practice, this is the most popular one. This is the most popular approach. So I think you read this many times either in master's thesis, PhD thesis, or IEEE publications. You did read it in many places. So this is one of the most important chapters. Okay, so now we are at 157. So if you like to listen to this class while reading your textbook, I think that would be useful. So that is the maximum likelihood estimator, which we call MLE. That is the very common abbreviation and is defined as the value of theta that maximizes the likelihood function. So if you uh, get a reading for this, it's a value of theta that maximizes the likelihood, and that theta can be referred to as many things. For example, DC level or sigma square or the phase in the sinusoidal, so on and so forth. You have many possibilities of thinking of the theta. Okay, and MLE is the one that maximizes the likelihood. The theta, the value of theta that maximizes the likelihood. Okay, and also MLE has a good property, which is it achieves the CRLB for high SNR. And you may wonder why. Um, Statistically speaking, it needs proof. It's not trivial. So, if you try to take the class in mathematics department, advanced statistics, there will be proof for that. But here, from an engineering perspective, what we want to do is we want to come up with a estimator that achieves CRLB, right? Because CRLB is the bound the bound that is, well, in some sense, if you have an estimator that achieves the bound, the estimator is the best one. Okay, so that's the way we think about it. um, Particularly from engineering perspective, you like to come up with a good estimator. More than that, you want to come up with an estimator that no one can do better than him, right? No one can do better. So what is the estimator? You are going to find the estimator that achieves CILB. Then you can confidently claim that this estimator is the best one. Okay. And then there will be some invariance property. And also a closed form expression for MLE, in practice, it may not be trivial, and a lot of times you cannot find a closed form. Okay, unfortunate. Unfortunate truth is that a lot of uh, good estimators is not in closed form. Then what's the difference between closed form and not closed form? Okay, if you find an estimator in closed form, it's a function of data in closed form, then that will be easy for calculation, right? You just pull in the data and do the closed form calculation, and you get the outcome, which is the estimated value for theta. That would be cool, right? That would be good. And the thing is, a lot of things cannot be in closed form. Then you need to do a numerical approach. Okay, so numerical approach is what, if you have uh if you have time, I would recommend you to do a good preview for the textbook, or maybe there will be a class that is called numerical approach 数值方法这一门课。我建议大家稍微看一下。Okay, but even if you don't take that class, I think you did it many times. For example, Newton approach. 以前在找函数大小的时候会用牛顿法，牛顿法就是一种数值方法，还有随机搜寻的方法，还有很多方法都是 numerical approach 的一部分，它只是在不同的名字里面。Okay, so like the Newton Raphel approach, convergence to MLE is not guaranteed. As you know, if you have some optimality to be searched, you use those numerical approach, it may not be guaranteed. But in some sense, we will take it as our solution because if we cannot find a better way, that is, that is at least in practice the best one, then we take it and live with it. Okay. Um, okay. So the MLE trying to achieve CRLB with high SNR, and then when does high SNR occurs? High SNR often occurs when you have a lot of data. You have a lot of data, and those data, of course, they are with the noise. The noise is independent. Then when you have a lot of data, they will be approach. Okay. All right. So that we finish this preview for maximum likelihood, and now we take a example. Okay. The maximum likelihood estimator. So let's take a DC label problem. DC label in white Gaussian noise. So it's in page 158. Okay, so this is the DC label problem in white Gaussian noise. And we consider the observed data set xn equal to a plus noise, and n is equal to 0, 1 all the way to n minus 1. That is the multiple samples, where A is an unknown DC label, which is assumed to be positive, and Wn is white Gaussian noise with unknown variance. This problem differs from our usual one, in which unknown parameter is reflected in the mean and the variance. But in here, uh, it's the unknown label as well as unknown variance. So that will also be the variance of Wn. Okay, so if you recall, it used to be the case where Wn has a sigma square, not A, right? But here we set it as A. So it's reflected in the mean and variance. Then in search for the maximum unbiased, minimum variance unbiased estimator, we first determine the CRLB, and the PDF is this PXA equal to 1 over 2 pi A n divided by 2, exponent of minus 1 to A summation. This summation comes from Gaussian distribution with multiple samples. If you have a single sample, then there is one exponent. You have multiple, you multiply by multiple exponent, and in the exponent, the multiplication becomes summation. So you get this summation. Then what we want to do is we take the derivative of the log likelihood function. Right, you take the log. Then as we mentioned, take the log. The meaning of taking the log is the meaning of taking the log is just to get rid of some complicated terms, and it's monotonic. Okay, so taking the derivative of the log likelihood function, we have this, and this is because you take the log and take the derivative with respect to a, and notice that there is a here, so it doesn't disappear. If it has sigma squared, then this thing will disappear, but it doesn't. It doesn't. Okay, so you get this, and summation of that plus this. And can it be turned into this form? It certainly is not obvious, right? It's not obvious. Can you get it into a visual information term with an estimator term? Estimator term is usually a function of data only, okay? It's data only. But you see there are a lot of terms that, you know, involves complications with X and A, so it's not trivial to put it into this form. Okay, it appears from a casual observation that it cannot. And therefore, an efficient estimator does not exist. We can still determine the CILB for this problem to find out, but we'll do it in the problem. Okay, so to find out the CILB is like this. So we next try to find an MVU estimator by reporting to the theory of sufficient statistics. Then we factor this into this. So this is from here, right? This is this term. This term you want to factor it out. 这是一个二次多项式把它解开来。So you get this. So that the PDF factors as this. Factors as this. You have this. You have that and exponent of this. Exponent of what? You want to put this term. You put this term, factor it out, and multiply out. So you get this. Now you see you get this term, and then n x bar g of x squared a. So it seems like we have put it into the Neyman Fisher factorization form. Okay, so uh, therefore, a single sufficient statistic A is Tx equal to that. Because of what? Because G, when you see G, you get this at a constant term. Okay. The next step is to find a function of sufficient statistics that produce an unbiased estimator. Okay. So I think we can, for this session, we just stop here and we'll continue next session.